Stanford University.
Welcome to the Seminar on People, Computers, and Design. I'm Terry Winograd. This is our next to last talk of the year. And if you're taking the course for credit, you will be getting an email describing what you need to do to make sure you get the credit. If you've been signing up on the sign-up sheet that's going around every week, that's all you'll have to do. But you'll get that. Next week we have Toby Grossman from Autodesk, who'll be talking about the learnability of applications. Ease of use is one of those things that we often talk about as though it were one thing, but in fact, easy to use once you've learned it and easy to learn it are two quite different things. And Autodesk, as you know, has a long history of very sophisticated high-use applications. So it'll be interesting. This week we have Anthony LaMarca from Intel, and I suppose it's no longer the case, but it used to be you would say Intel and say, is he going to talk about chip designs and architectures? And it's been the case now for many years that Intel has a really interesting and active research activity on not how to build those chips, but what people might do with them. So a lot of you may have heard Genevieve Bell talk here last year, who's anthropologist, does anthropology, but about people's using devices, and is one of the best known people in that area. Eric Dishman has a large group doing health. You may be talking about some of the stuff that his group does. So it's been the case, and I'll make a general, what's the right word, sort of analysis here, which fits twice in Anthony's case, which is when a company has a big enough share of the market, but don't call it a monopoly.
We can't use the M word.
They have the luxury, let's call it, to actually do longer term research. They aren't stuck with what wasn't happening next. Before he was at Intel, Anthony was at Xerox PARC, which was the great example of that from a few decades ago when Xerox had the whole market in copiers and they were able to do a lot of really interesting research which they didn't actually capitalize on. Although they did. That research led to their printer business, which is not bad. But certainly the whole personal computer industry. So I'm really glad both that Intel is doing this kind of work, and Anthony's going to be talking about sensors, something which obviously is very relevant to their business. As you know, computers are now able to sense things that are a wide variety of environmental things, and we can make use of that in new and exciting ways. I'll let him go from there.
Wonderful, thanks. Dude in the back, if the microphone's not working, let me know. I think I hooked it up right. Right, so as Terry said, I'm going to talk to you today about some fundamental, largely open-ended research around the area of sensing and sense-making, really sort of in pervasive or ubiquitous computing systems. I know this is an HCI venue. I'm not an HCI expert, and so this is really going to be an overview talk of the research center that I'm working in, but I'm going to try to make a couple of serious, if sophomoric attempts to actually try to think about the HCI implications of the work that we're doing in the center. So, right, as Terry said, Intel does have the luxury of investing in some further out, not immediate research, and just this last year they started a new series of research centers with, I would say, a relatively new model as it pertains to how industry collaborates with academia. They're calling them Intel Science Technology Centers. It's $2.5 million a year for 5 years, so it's enough work to fund. It's enough money to fund the work of about 30 to 35 grad students. They're doing it at multiple universities per center, but they're doing it with a host university. It's sort of, they're calling this a hub and spoke model. So they're choosing for a given field, so say for instance, visual computing. There is one of these centers here at Stanford. They chose Stanford as the hub of the visual computing center, but then Stanford basically chose collaborators from other universities to pull in, but Stanford sort of serving as the sort of the warm, chewy center of it. The idea is to encourage collaboration among the best in the world. The part that I think is cool and kind of unique about this is in each of these centers, with the exception of Stanford, because they're still kind of, it was the prototype, there are up to 4 Intel employees, Intel researchers that are actually co-located at the university. So I have the great fortune of actually having an office in the Allen Center at the University of Washington. And it really sort of tightens the bridge between what's happening between Intel and the university. And the IP model in these centers is really explicit, that all the work is published, none of the work is patented, and we're driving everything towards an open source license that's really amenable to commercialization by the students and by Intel. So everything's being released BSD if possible. So there are 5 of these centers now. There's 2 more that are shortly going to be announced, but I don't want to say on camera. There is one here that's being run by Pat Hammerhand at Stanford on visual computing. I'm part of the Pervasive Computing Center at the University of Washington, and I got to talk about any of the rest of them. So just to say a bit about pervasive computing, it's had a fabulous string of successes commercially the last few years. I mean, this is sort of pictures of all of these products. This slide's a little dated. I'm sure I could come up with newer ones. That really represents the culmination of a bunch of work over the last 20 years to try to take sensors, fit them into mobile devices, or embed them into the environment with things like wireless networking and applications and usages that sort of open doors to things that we don't traditionally think of as computing. Measuring your running pace is not something that 20 years ago we thought of a computer as actually doing for you. And to a large extent, this has been hugely successful. And I want to say, not to criticize my community, but I want to say we've been kind of, I would say, resting on our laurels or coasting a little bit. More and more of the papers that you see at Pervasive or at UBComp are, it's good work. They're enabling new applications, but they're doing it with the sensors on an iPhone, and they're releasing the app on the App Store. I mean, a lot of these talks end with, and go ahead and download from Android Marketplace. I think we need to pick our sights up, push a little further out, aim for something that seems, a lot harder, seems as hard as building something like this did, back when Weiser was starting the stuff at Park 20 years ago, and try to invent the kind of the next generation of pervasive computing infrastructure. So we have a mission here to try to build systems that are much more richly aware of people's lives than they are now. Try to infer things with more detail and more depth. And I'm going to get into this a little bit later, but one thing we really want to shoot for is building systems that learn and adapt over time. I think a lot of people confuse personal with personalized, and they're not the same thing. So we have the whole breadth of pervasive computing to investigate, but we're choosing to invest our resources and our projects in the areas where we see potentials to really make a difference and have a tipping point. Some things are being miniaturized, some things are being changed or sped up in ways that are just very predictable, and they're going great for the field, and so we're just not messing in those. But these are the 3 areas: low power sensing, new algorithms for understanding human state, and personalization and adaptation. That's where we really see the opportunities. I'm going to go into each of these in a slide later on. And feel free to stop and interrupt me and ask questions if you want. I like interactive. So this is an interdisciplinary center. I mostly put this slide up because, I work with a group at Intel of networking people, and they claim they're really interdisciplinary because they work on both physical layer and MAC layer issues. But the thing that makes this center fun is that these groups of people don't go to the same conferences. They don't actually publish together, and trying to actually get a computer vision person to think about power harvesting or to think about the HCI challenges is yeah, Leslie.
Disciplinary or interdisciplinary? Because it seems like a lot of these are computer science. So
it's true.
About your collaboration.
Yeah, I know. I shouldn't be quite so holier than thou about this, but.
But are there specific verticals that you're focusing on, like other departments or fields that?
No, this is pretty much it. I would say, compared to these other ISTCs, compared to the one on, security, or the one on cloud, or the one on vision, I would say this is them. We're having the most challenges integrating our community. So, but yeah, no. Good call. So to try to sort of get all these people together, we're sort of doing the standard trick of coming up with a couple of sort of key capstones, key scenarios that we want to sort of say, well, let's collectively build a system that does X, and then sort of those requirements force people to think about each other's issues. Old trick, but so this is our research team. You can see most of the faces are associated with the Northwest, and that's because the center is housed at the University of Washington. There's the 4 Intel folks, and we have 9 UW faculty, ranging from vision and machine learning to James Fogarty is our local HCI guy, and Dieter Fox is the PI of the center. He's the Pat Hammerhand for our research center. Fei is part of the center. Her work on fine-grained object recognition and now branching into activity recognition is really central to some of the challenges that we want to solve. So we're super happy to have her involved. Also on the West Coast, we have Deborah Estrin working on a lot of mobile systems issues, and she's lately had a real interest in health applications and health services, which fits well with pervasive computing. Two folks from Georgia Tech, Jim Ray's a vision guy, and I'm sure most of you know the work of Gregory Abad. And then Tanzim and Henry do machine learning and AI as part of the center. And thus far, other than the issues of sort of dealing with 6 schools, I'd say that the multi-school aspect of this has worked really well. We really were able to pick a real kind of dream team to do this work. Okay, so I wanted to actually try to say something that pertains to the topic area of this venue. And so I started thinking about HCI and pervasive computing and what it means. And of course, other people have thought about this before. So I went digging around, and I reread a really excellent paper that was written by Victoria Bellotti and company more than 10 years ago, making sense of sensing systems. And it's a paper that took Don Norman's 7 stages of execution and tried to adapt it to a pervasive computing system and say, well, what are the stages of execution in a system that actually has embedded sensors that a user interacts with in what you would consider to be non-traditional ways. So they came up with 5 stages of execution, and these are all stages that involve communication between the human and the machine itself. So this is not stages of execution in the sense, now the computer reads this data off the disk, but the stages that involve the actual human interaction. There's frightfully clever people, so they managed to make all of them start with the letter A, which is always great when you do these kinds of papers. And I found these stages really interesting, and when I reflected on what we were trying to achieve in our center, I had some interesting revelations to me. So I thought I would share them as I actually go along with the overview. So the stages that they identified were first that when you have a non-traditional computing system like this, you may have to have sort of new techniques for actually directing communication into the system. The problem they call address. I mean, there isn't a mouse, there isn't a keyboard. So the most basic problem of how do I even address the system? Do I do it in a new multimodal way? Do I have to go somewhere and do something traditional? And even if I know how to address the system, the second issue here is, well, how do I even know that the system's listening to me at this time? How can I tell it's on? I don't have the blinking cursor that you would have in a traditional system. Similar to the first issue of address, even if I know how to address the system, I need to understand how to communicate different types of actions to the system. I'd like to tell the system what to do or direct it in some way, so there has to be a language, there has to be a technique or a mechanism for doing that. Probably the issue that I'm most concerned about is this fourth one of alignment, which is, I think, to be successful in sort of this relationship between a person and a system, the person has to have some idea of what the system state is and what the system's actually doing, and whether things are sort of going in the direction that the person thinks it is. So in effect, sort of communicating the system's state to it. This is what they call alignment, and I think this problem is going to become more important going forward. And then the last one is accident. This is maybe the A word they kind of squashed in the most. And this is acknowledging that we make mistakes, and that sometimes you need to halt a system or stop it or even undo some action. And so the system has to support some facility for that state of execution. And so thinking about those 5 things and the research that we want to do, I should say, some of the work in our center that we planned out is explicitly aimed at HCI. There are some things we're explicitly trying to make better via the technology we're going to invent. In other cases, we're trying to enable something completely new, something completely different, enable a form of, say, mobile health monitoring that doesn't exist. So our focus here is not on the quality of the HCI, but rather on, say, improving someone's health. In that case, we may actually create some new challenges around HCI by virtue of the technology we make. So So I thought about the research themes and the research projects that we're working on and realized that in some cases we're actually developing some good solutions. So we're actually going to make some of these stages of execution better if we're successful in our research. In other cases, we continue to have a reliance. So much like Victoria and company identified that there was a gap in some cases, that's a gap that still really needs to be solved for us to fully utilize the things that we're inventing. And then probably the most interesting ones where I sort of looked at what we were doing and realized that we were actually going to potentially grossly exacerbate some of these problems and make them even harder to solve. So I'll point those out. Any questions? Give me one more second. Okay, so the first theme of our research, and I'd say the three themes have sort of, I'd say approximately, this one's a little on the smaller side, but they're sort of roughly divided up about a third in terms of the faculty and the students. So the first one is around enabling much more continuous and unobtrusive sensing. So putting sensors in places where they didn't go before and having them run for very long periods of time. When you start thinking about this, you pretty quickly get to the fact that you don't want to plug them in and you don't want to have batteries. And so we've got a big push within our center on power harvesting. And here we're looking at harvesting in a pretty broad scope, moving beyond, you kind of think of solar as a pretty high, highly available source of energy, but then you can't take the sensor and embed it in an object. You can't put the object in a container. So we're looking at lots of things like RF harvesting from radio, harvesting from vibration. One that I'm frightfully interested in, just because it never occurred to me, is the atmosphere. Like literally, the air around us exhibits the same tides as water. You don't think about this, but the air above you gets heavier and lighter and heavier and lighter twice a day. You can actually harvest energy from that. Enough. These are very small amounts of energy. There's in some cases, tenths of microwatts. But as I'll show you later, we've been able to build circuits that save that up and then save up just enough power to read a sensor, do a little computing, and send a radio packet. Enough to make an object part of this whole Internet of Things type thing. Terry?
I was curious about your scope here. You say awareness of people. And so these same problems happen, let's say, if you're putting sensors in buildings for stresses, for earthquakes. Or
Sure,
something.
yes.
Are you working with that, or is it sort of that's a separate bunch of stuff?
I think that the technology applies widely in both cases. We're explicitly not working at all on things like building monitoring or figuring out how many birds are in the forest. I mean, everything in ours involves human activity. We don't really only care about human activity. I mean, to the extent that we can infer human activity, say, from the temperature profile in your home, then we are interested in, but we don't care about cracks in bridges. But they do share a lot in common. Probably the piece of this that I'm most interested in is this idea of building perpetual systems. So there are people working on low power radio protocols, lower power sensors, power harvesting separately, but viewing it as a system and saying, if I'm harvesting power at this rate, I can afford to duty cycle the sensor with this frequency and send a packet this often and build a system that really truly perpetually senses. So this is something you just, you deploy it and then it runs forever. The amount of data you get is variable because it depends on how much energy is available at the time. But I find this idea really exciting, and establishing a baseline with this generation, I think would be valuable. So, reflecting on this now in the context of the 5 stages of execution, I realized a couple things that. In this case, if you are deploying small sensors into sort of everyday objects, we still have the problem of how you actually address them. If everything's instrumented, I still don't necessarily know sort of the right way to actually direct communication to the system. And so that's a problem that still needs to be looked at. The big problem I saw here was this notion of attention. So sensors that are already invisible are already going to create a problem. If I learn, for instance, that things I do in my gym automatically appear, back in my health assessment at the end of the month, I'm going to develop that understanding and that model. And power harvesting means that you're getting different levels of attention, potentially no attention, if the system isn't able to harvest power. Actually having sort of varying amounts of coverage and brownouts and blackouts, I'm concerned that this is going to result in sort of a deep lack of faith in a sensing system by a person if we can't solve this. Yeah?
Just one more scoping question. Are you talking about ambient sources? Are you focusing on not on-body system, or it's on-body as well as ambient? A lot
These-
of our harvesting stuff has been,
No. This is ambient, mostly thinking about deploying in the home. I mean, so you put it in a baseball, and the baseball is going to get a lot while you're actually playing with it. But we want it to harvest energy even when it's sort of sitting in the toy box. Yes. No, not the shoe. That actually turns out to be a lot easier, because people move around enough that if you just do the kinesthetic stuff, you can generally do pretty well. Yeah. No, we're looking for ones for objects that don't move much necessarily. Good question. So our second research theme is around understanding human state and activity. We're going to call this theme context awareness, because that really is what this is about. It was a very overloaded term at Intel in particular, and so we wanted to be really explicit, and I actually like this better. This is really about developing algorithms that, from sensor data, can basically extract an understanding of what someone's doing and what objects they're interacting with, and how they're situated in their environment. And here we're trying to push beyond, I would say, the sort of typical, just what I call kind of the generation 1 sensors of accelerometers and radio signals and GPS, and also start to pull in the newer sensors like the Kinect style depth cameras, and think about how you actually model them together and jointly to really provide this sort of rich awareness. Right now, you can certainly sort of see some papers and see some videos. I'm going to show you one, and so we can show this in many cases thousands of times slower than real time. So actually developing these algorithms and actually getting them so they run real time, potentially even on mobile devices, I think is sort of the scope of a 5-year challenge. I should say now. So this center only started last November. So I'm giving the overview of most of the problems that we're going to look at, and I'm going to touch on a few little sort of research nuggets for results we have that are forthcoming. But for the most part, this is kind of we're just kind of starting out. When it comes to these 5 stages of execution, I think we potentially offer some promise, specifically around the area of how you address a system and how you direct actions to a system. We're really hoping in this to develop deep capabilities in multimodal interaction and being able to point at objects and talk and have the system interactively learn your gestures and learn new objects. And hopefully addressing a pervasive system should get better if we're successful in this. The thing that makes me nervous as someone who has written systems that have an end user facing component is that increasingly the system is modeling everything as a probability distribution, maintaining sort of a large number of possible hypotheses about what's going on, and potentially weighing those actions all in parallel. And so when everything becomes probabilistic, it seems like it becomes even more difficult to express the state of the system to a user. We've gotten good at it in a location system where we understand sort of how to put halos, but what does that mean for sort of everything that one of these sensing systems is doing? I don't know. That makes me nervous too. And then the last research theme we have is personalization and adaptation. And the idea here literally is to have a system personalize and adapt itself to you over time. As I was saying, personal and personalizing are not the same thing. You can have a personal device that measures your step count as you go through the day, but the systems don't exist today that actually get better at measuring you as you use it over the course of time. Both in the system improving its own performance and sort of more and more accurately recognizing, say, your objects, because it knows that that is your coffee cup. It knows that's your coffee cup, so it can move beyond a general purpose model of a coffee cup and tailor it to the 17 mugs that are in your house. But also potentially being extended by the system to be taught things that it didn't actually know, new types of activities and new types of objects. Again, I think personalization and adaptation bring value to figuring out how we want to address systems and how we want to tell systems to take actions. Different people are going to want to interact with systems in different ways, and it may be okay then to develop fairly generic artifacts that then sort of very quickly figure out that, this is somebody who really prefers this form of interaction. I'll really focus in on that and sort of throw fewer false positives, say, when they do other things. Learning systems in general make me nervous. Systems that behave totally differently today than they did a month ago, especially around when the system does unintended things. And I'm especially nervous about what happens if the system actually chooses to adapt its model or grow its knowledge of you from erroneous actions. So what happens when bad training data actually gets into the system, and how we actually back that out. For the most part, machine learning and vision people just ignore that now. They assume perfect ground truth when they actually train. So kind of a mixed bag, I would say, from an HCI perspective. Yeah?
Do you think the larger risk is accidents and not alignment for personalization, and it is alignment and not accidents for the probabilistic activity modeling?
I think alignment's already a huge problem back here. So I suspect personalization and adaptation make alignment even worse. You're totally right. But I just figured it was already going to be so bad after we have these, after a system switches over to sort of maintaining these sort of large numbers of sort of parallel hypotheses about you, probabilistically. So what was your comment about accident?
So why is accident not important for, let's say, a probabilistically modeled activity, probabilistic activity model, the previous theme that you
Well, assuming you can communicate it. So let's say, I'm just making all this up. Let's say, you're cooking something and you grab a cucumber and you start chopping it up and the system accidentally thinks it's an apple. But the system can say, gee, this is what you stop and you say, what's going on here? Why is this not acting the way I expect? And the system says, well, these are the 5 things I thought it might have been. And it says, and so I really drew the conclusion it was a cucumber. If it was an apple, you can at least then potentially have a model and say, okay, I understand why you made this mistake. So let's sort of back up one. I'm especially nervous about accident here because I don't know I actually don't know how learning systems behave when they actually get bad training data. I don't know what happens when the model becomes personalized. Everyone's sort of had a spouse or a sibling go off and use their Amazon and buy some gifts for you, and from that point on, your profile is just desperately screwed up, and it's suggesting, in my case, My Little Pony every sort of third page, and because my kids bought stuff once, and so when that suddenly now involves your actual sort of day-to-day, HCI, I don't know, I'm nervous.
So
I said my analysis was a little sophomoric, so.
So which of these two models is closest to what you think? It's in your house, it knows it's you. It's in your gym, and it has to recognize you when you come in the door. It's different for everybody who comes into the gym, but it's
I think the latter is definitely what we think of when we're talking about personalization and adaptation. The same sets of sensors, potentially the same end goals, but it's doing them in different ways because you behave differently within the context of the system. Does that answer your question? So I said, I think near the beginning, that we've got 3 capstones, and I'm going to touch on each of those and show you some sort of initial results that we're getting for them. What I want to say about them now is that we actually are looking at pervasive computing at 3 different scales on purpose because they have a different set of challenges. So probably the most difficult deployment environment is the whole world. In that case, really the only thing you can kind of really count on that someone has with them these days is a smart device, and then they've got some cellular infrastructure for some networking. But by and large, you've got to do all of the inference that you need to with this mobile device potentially acting, as Terry was sort of saying, as a hub for maybe a couple of sort of body-worn accessories like a Fitbit or a shoe sensor. So in that context, we're looking at a mobile health and wellness application, and the challenges here really are around how can you infer rich things from a pretty limited set of sensors, and how can you make it power efficient, because this is a device that has some serious challenges right now. I mean, this device is efficient and runs multiple days largely because it's asleep almost all the time. That's what the GSM guys were very, very clever at doing, and these workloads are sort of largely always on and sensing, and so huge power challenges there. When you constrain the environment a little further and say, well, now I'm going to get just inside the 4 walls of my home. Now you can afford to actually deploy sensors more widely, right? It's a small world, but I wouldn't want to paint it. So you can't put sensors everywhere. But once you get into the home, maybe you can. So now we should be able to up the expectation for what we can infer. Now privacy issues become become much more important, and now you're inferring things about multiple people at the same time. So I'll get to that. But the multi-person aspect. In the first case, a lot of it's largely personal because it's your device and it's on you. We go one step further in our third capstone, and in some sense this is the one I'm the most excited about, which is to say, well, what if we constrain ourselves more narrow than the home and we pick one small area, something that's only, say, a square meter, and it's a space that's used for a very narrow set of tasks. So something like a kitchen counter or a shop workbench. In this case, you can you know a lot about what activities are done there. You can deploy a very dense network of sensors, a half a dozen Connect cameras pointing down at a section of kitchen counter. So you should be able to infer things, with a very fine level of detail and with a very high level of accuracy. And so we're looking at that as well. So the three scopes and scales. So on the mobile health and well-being, this is primarily being driven by Tanzim Chowdhury and Deborah Estrin. And the idea here is to help people identify, manage, and reduce stress in their daily life. So you put the device in there, it learns actually what you find stressful, and it figures out when it happens and provides, hopefully, interventions and lessons so that you have less of this. The real jump here from the first sort of, I would say, generation is that what Terry finds stressful in his life and what I find stressful may actually be very, very different. He may hate crowds, I may love crowds, and so this is a system that's going to sort of ultimately fail if we don't actually get the personalization right. So that's kind of the real lever here, and then of course making it run over long periods of time. I want to just do a quick.
Go back to that.
Yeah.
What are the key data entry things that tell you what stress level is?
So Tanzim is working with colleagues at Cornell to do stress from voice. So literally, what you're saying evidently has enough features in it to actually detect your stress level. So I think measuring stress is not the challenge, but the real challenge.
Much of my stress comes while I'm sitting at a keyboard.
So maybe they only get your stress then when you're on phone calls that you get when you're on your keyboard. So yeah, they're explicitly trying to do stress from voice. We've done a little bit of work looking with a galvanic skin response to like a GSR sensor, but I think they don't want to rely on that. So I think that's a secondary sensor they're looking at. The trick then is trying to figure out what are the daily situations that cause you stress. So when you're stressed, what was happening, and then learn those and recognize those patterns, and then figure out when you're about to get into a stressful situation and say, hey Terry, this next meeting you have at 2 o'clock with that guy, you always get stressed in this meeting. Let's try these techniques before you go in. It's so this isn't a project explicitly about recognizing stress, but actually trying to predict and mitigate it. It's a 5-year challenge, right? So I think they're going to be the first year probably getting just the stress measurement accurate. Although this is a screenshot from a system that they just released on the App Store, on the Android thing, BeWell, that apparently does do some stress analysis. So OpenEM Health is a system that Deborah Estrin she sort of brought it into our center because it's sort of IP compatible, and she's one of the co-founders. It's not all her, but it's explicitly about component architecture for mobile health applications. So people can supply visualizations or data analysis blocks or new ways of collecting sensor data. And the idea is really to sort of tear down the stovepipe and let health practitioners sort of very quickly assemble these sort of types of mobile sensing applications. And she's got a large number of health practitioners on board that want to do deployments. This is a screenshot from a post-traumatic stress disorder coach that they're actually deploying not in Iraq, but in the field with Iraq veterans that have come home from the US. So it's very exciting. I don't think actually BeWell is deployed on their system yet, but it probably should be. So our second capstone is around family coordination, and here the app itself, frankly, is a pretty thin veneer on top of just the activity detection. So we're trying to look at the problem of family coordination and helping people coordinate busy lives. The real challenge here and the real crux, if you've ever gone and read any of these papers, which labs like my own or others have published around activity detection in the home, this is used a lot for assisted living, ADLs, early stage Alzheimer, you'll see that most of these systems are for single occupant dwellings. They're very, very good at detecting a single activity at a time with a home that has a single person living in it. because when people coordinate on activities or people interleave activities or when they sort of collectively work to achieve a task, it is very, very, very hard. Sort of, I would say, not possible now to successfully infer activity and intent. So the real challenge here is using sort of the wide variety of sensors we have available, infrastructure sensors as well as ones potentially in your mobile devices, to try to jointly reason about a group of people. We're looking at a family in this case, although I think this would work just as well with, say, a research group at a university or a work group at home. But doing multi-person activity modeling. Yeah.
I'm having trouble with the abstraction level. Give me a poster child for the kind of activity and the kind of help a computer can give that makes this really worthwhile.
Susie is packing her bag for lacrosse this afternoon. The system figures that out based on sort of the object she's picking up and what room she's in and how she's going about it. You're downstairs and it looks like you're packing lunches for 2 different people. Your wife is still sleeping and the system thinks that collectively you're all 20 minutes behind schedule from your usual routine based on the current status. Things like that.
So then it yells?
It could. I'm not sure I've quite thought out exactly what we do with it, but the idea of going from the very small sort of simple activities, like making a sandwich, all the way up to something as complex as, this family is 20 minutes behind schedule from where they usually are on a Tuesday. I think that's a sort of a huge leap from a machine learning perspective. The models they need to develop for this are and to have it actually be robust. I think that's a giant challenge. What we build on top, I think we just have a lot of faith that that's going to be a really, really useful capability. I can't actually really kind of testify to how great I'm going to find that out myself personally, because we're always 20 minutes behind, so that's not new to me. Yeah.
A lot of these home activity sensing systems, they work in a North American context where you have different places in the home meaning different things. I'm wondering how you plan to scale these to, say, an Asian context where houses are small and lots of activities happen in a co-located manner.
I think we're actually not using location a lot. I mean, I would say you'll see later with a couple of videos a really, really strong piece of what we do. Like the real grounding is actually objects. So the objects that people are manipulating and how they're manipulating, literally the trajectories you move objects around, it says an awful lot about activity. So I don't believe we're actually grounding anything in place yet. So here's, I just wanted to put up here, so this is an example of one of those power harvesting sensors. This is an early one. It was actually, it's a sensor that measures CO2, or carbon monoxide actually. And the thing I like about this is that this is a sensor that's capable of taking readings periodically and then communicating them over 2.4 gigahertz radio. And it does it all with power it just harvests from television signals. So literally KTVU channel 2 is sending enough energy, blasting it over your neighborhood, that you can actually harvest enough energy to power what's in effect a very small computer and actually do sensing and return it. This is this antenna is a hideous form factor because I think they got it at Radio Shack for $7 or $8. But I've been assured that at the cost of some efficiency, it can be made much smaller and much more embedded. So it's sort of an interesting example of an artifact that does power harvesting. Another sensing modality, I wanted to do a quick touch on the work of Shwetak Patel. I don't know if folks are aware of the work. Oh, he did? Great.
When was it? A couple quarters ago.
Maybe like a year and a half ago now.
Yeah, okay, so he kind of pioneered this idea of infrastructure mediated sensing, which I really, really like. And this is the idea that homes have infrastructure. Things like it has power lines running through the walls. You've got pipes running all through the house, and people interact with this infrastructure all the time. Every time you turn on and off a light, every time you go and flush the toilet, you're using this infrastructure, and it's actually quite easy to measure that infrastructure at a single point. So you measure it at the water main, or you measure it at the switch box. And what they showed was that the different, I would say, points at which you interact with that system. So every light switch, every water faucet, every device actually uses the resource uniquely, and therefore you can infer its use by seeing its signature on the power line. So every light switch actually leaves a different little bit of noise. And so infrastructure mediated sensing has been shown to accurately infer that people are using a very small device. You can kind of think of this as a building block. And so this is their first step to actually take that type of data from infrastructure mediated sensing and try to actually step back and infer activity from it. Because the truth is we don't really care that light switch 72 was turned on and off. What we want to know is, Dad successfully got himself dressed and out of the house today. And so therefore I don't need to call the day nurse to go help him. And so they did a trial this last quarter in the Georgia Tech Aware Home with HydroSense. That's their water system. So this is a sensor that simply measures how much water is used, and from it they can infer which faucet's being used. And what they showed, and I was actually surprised, I didn't think that these results would be this good. They showed that just with the single sensor of how water was being used, they could distinguish, depending on the number of participants, between 70 and 80% accuracy between 11 activities. Obviously water-related activities. But things like they could distinguish shaving from washing hands from filling a kettle. And this is just a single sensor. Obviously, we're going to want to do something very multimodal and involve objects and potentially lots of other things. But I found this encouraging. And then our last usage is the one that is the most constrained physically. So now we're restricting ourselves to a surface that's small. And the idea is that we want to actually show that we can do task assistance. That's the usage here. We're grounding this in a kitchen scenario because lots of people cook, and it's sort of a classic. It's a classic Chi UbiComp type usage, and we want to really advance the state of the art here and try to build a system that not only provides assistance, suggesting that you need to stir that more, or that you're missing an ingredient, but actually allows new recipes to be taught to the system. So you could actually say, look, this thing's called a rutabaga. I'm going to show you this, chop it up, you do this, that, this, and we're going to call this recipe this, done, and have the system integrate what it could see, what it knew, and what it heard from you to actually create a representation of that activity that could then turn around and be taught to someone else. So that's kind of we want to sort of close the loop and actually try to show this by the end of the center. This is a huge way to go, so what I'm going to show you now is definitely baby steps. But I wanted to take, I'm doing okay on time, I wanted to take a second and show you, now these are older videos. So this is stuff that actually slightly predated the center. This is part of what got Dieter and I so excited about the idea of this sort of sensor-intensive task space. This is a system like the one that we hope to develop that has a coupled camera and projector system. This is using really rudimentary object recognition. In the case on the left, this is a usage around the kitchen. On the right, this is, I don't know if anyone saw this work. Do you know where this was shown, Scott? Was this shown at Chi? This is a video from an Intel demo at a tech conference. This is around Legos, so toys. So someone puts down the building and a road appears in front of it to put down the dragon, and now there's fire, and you know what happens if you put the dragon too close to the building. And it's the same system, but just a sort of a different usage. One is around interactive toys, and the other is around kitchen. What I actually realized when I was putting these slides together was that this type of a system actually has some built-in solutions for things like how you address the system, how you know the system's paying attention to you, how you communicate actions. But actually, because we have the luxury of using a projected interface, we've kind of got this augmented reality. A lot of the same things like cursors and prompting and all of that can actually apply. So I think from coming back to those 5 stages of execution, this capstone probably actually has the least issues, raises the fewest challenges. A lot of the existing stuff just kind of works out of the box. That was not a system that was doing any learning. It had built-in models. It was. So, I want to talk to you about 2 more other little things that we're looking into. something that's going to be new about the system is the idea of doing interactive grounding. So grounding is the idea that you take a model, say a model that can be recognized as an object. You actually ground it to a label. So you sort of teach the system this is an onion. This is typically not done interactively. Typically, the system is trained offline, and then you deploy it. And this is our kind of first attempt at doing this personalization and adaptation. We want to do interacted grounded learning. So something where you can actually have an object and set it in the scene and then say, that's an onion, and the system will parse the natural language, it will build a model of it, and then it will actually associate it, and from that point forth, it will incorporate it as a real first-class thing. Going beyond that, once it knows what an onion is, then you could actually say, I'm dicing this onion, and it would sort of associate dicing with the actions that you take that it observes. And in a similar way, we want to try to integrate what's happening with the camera with the spoken language in order to solve problems like defining quantity. So it's actually quite hard to tell from vision. I've been told impossible, but these guys are so good. I don't believe it's impossible. But if you take a cup and you sort of fill it 3/4 of the way and then pour it in, it's just nearly impossible for a vision system to realize that you're actually putting in, say, 3/4 of something. And so the idea of actually picking quantities out of the spoken track and then grounding it in the objects and associating it as an attribute of the object that you're manipulating at the time. And then and then the flip side of this is actually we've been using the language a lot to improve the vision, but you can actually turn it the other way around. When you talk to a natural language system, it's probabilistic. It's deciding among lots of choices. The context and the objects that are in the scene actually let you help sort of refine the vocabulary of things that could be. So actually, by grounding these two together, you actually get higher quality, better accuracy recognition of the natural language. Yeah.
There's the emphasis question here about, this seems to imply that you're not trying to instrument the objects in the setting, but you have a camera. So for example, if you said to your great guys there, build a cup that can tell you how full it is, instrument the cup. They could do it, right? That's not hard, but then you have to have the special instrumented cup. Or if you say, let's put an accelerometer in the knife, dicing is going to be a very clear pattern on the knife.
That's a great question. So it really depends on who you talk to. So by and large, vision researchers are purists. We had to drag them kicking and screaming to the depth camera because it wasn't a traditional red, green, blue camera. They didn't like the fact that it had this new depth channel. So I mean, I hate to tell a story about Xiaofeng, especially it's going to be on YouTube. But so Xiaofeng did not want to work with depth cameras. He's a world-class segmentation guy. And so we actually gave him a data set and said, do the best job you can segmenting these images, these objects out of these images with a regular camera. And he did. And he did a great job. And he actually managed to achieve the goal of over 90%. But we gave the same problem to an intern with the same video, but it had depth data in it now. And he also achieved 90%. The difference was that Xiaofeng's algorithm was literally 5 orders of magnitude slower. So his was like 1,000 frames per second, and the other one ran at 10 frames a second. And then he was convinced. He said, fine, I'll work with this new camera. But getting them to sort of accept the solution of saying, well, we're just going to have a very nice little E-field sensor, electromagnetic field sensor in the cup so we can detect the height of the liquid. They hate that idea. I think the sensor researchers like Josh are going to do that, and they're going to put them in the scene, and we're going to sort of force them to do some joint modeling. It certainly makes the problem easier. Yeah. But the stuff we're showing you now is trying to do it in a totally uninstrumented way. To be fair, none of these sensors will go through the microwave. A lot of them are dishwasher safe, but you just can't put the electronics through the microwave ever. So they fall back on that and saying, but you can't put that spatula through. Yeah. Can you microwave RFID? No. But you can't put it through the dishwasher. Yeah. Okay, so the last thing I'm going to show you is our first attempt at actually doing activity recognition with a depth camera. Object recognition is coming along pretty well. They've moved beyond sort of SIFT and SURF as 2D image features to sort of starting to incorporate depth-based image features, so they can do a much better job. And the depth camera, so the problem of segmentation is the problem of picking an object out from its background. So sort of knowing that this is the, this is the thing, and to throw, like if I have a loud shirt on, I always have a loud shirt on. The depth camera makes segmentation like near trivial. You just sort of chop off any pixels that are beyond a certain thing, and objects just pop out. But this video is going to show you that we're actually starting to be able to detect activities, which is interesting. So this is a video of mixing some cake, and I think it's putting labels. It's putting labels on the objects, and that's not super impressive. That's been done before, but we're tracking the hands in 3 space, and when the objects get near enough to, when the hands get near enough to the objects, we actually, assume that they're manipulating the object, and then at that point, we actually have a library of object-specific actions that can be taken with it. So, for instance, spoons can scoop, spoons can stir, bowls can have things poured into them. Eggs can't have things poured into them, but eggs can be put into something else. And so, based on that set of knowable actions, we take the trajectories that the hands are moving through and try to match it to the trajectories that are known for that action. Yeah?
Is this real-time or post-processed?
This is almost certainly post-processed. Yeah. There's no way. I don't know for sure, but I would bet it's not real-time yet. And in general, this works pretty well. I think it's about 90% accurate. The thing I actually found interesting, and this is where I completely deep-ended with Fei-Fei's students this morning talking about this, is the object recognition itself was really not that good because lots of the objects look the same because they're all sort of white porcelain. The object recognition was only about 40% accurate, frame to frame, but functionally, it was almost 90% accurate, meaning that when they made mistakes, they often mistook an object for an object that had the same function, because a lot of the form, a lot of the function is sort of due to the object's shape and its form. So this idea that maybe we shouldn't actually be quite as focused on recognizing exactly what an object is, but more grounding the recognition in what an object is good for. Because that was an interesting idea. And then my last non-wrap-up slide was I talked about OpenEM Health, this open source framework for doing mobile health applications. I wanted to mention 2 other large, mature, sort of excellent projects that were brought into the ISTC by the faculty participants. So the Aware Home, for those that don't know, it's one of these living labs. It's a 2-bedroom townhouse, instrumented 9 ways from Saturday, that's off campus in Georgia Tech that actual people can live in, although I'd be really scared, but I think they pay people to stay there for long weekends and collect sensor data. We have a big data set we're collecting there now for kitchen activities. And the last one is one from right here, and this is ImageNet that's been done by Fei-Fei and her students and postdocs, and they have this sort of incredibly detailed image ontology, not just saying that's a bird, but actually telling you that this is a male oriole in its sort of 3rd year of life and hasn't molted yet, but really super, super fine-grained object recognition. So I wanted to wrap up and say that the goal of this center is to try to develop kind of the next generation of infrastructure for pervasive computing applications. We're focusing an awful lot of the attention on this on algorithms specifically for context awareness and personalization and adaptation. And when I think about those, I think from an HCI perspective, the implications are kind of mixed. That I think there's going to be a richness and an accuracy to interaction in non-traditional ways that's going to be good. I think some things that are 50% accurate now are going to be 98% accurate a couple of years from now, and that's great. But just the amount of monitoring and the dynamic nature of the system and the coverage is going to, I think it's going to present a lot of challenge when it comes to communicating to users what's going on. So I don't think this community is going to stop thinking about how to support pervasive systems anytime soon. Thanks.
Most of your slides talked about sensors as input to an ubiquitous computing system. What do you think we should be doing for output? And how do you think we should get that?
So let me just ask the question back to see if I got it right. So you're saying that a lot of this is focusing on how the system senses the person. You're wondering the other way around, what modality should be used for the system communicating to the person? That's interesting. That's a good question. So reading through that 2001 paper, I realized that I don't think Victoria and Becky and Keith and the other authors on that paper, I don't think they quite understood the extent to which pervasive computing would be used for passive monitoring. So an awful lot of what the systems are being used for now is watching someone in order to collect data to then at some point in the future sort of summarize and present back to them or to someone else. So in the case of, for instance, the mobile health monitoring applications, let's say you want to count your steps or you want to your smart pacemaker that you're talking about at lunch. A lot of that doesn't necessarily involve large amounts of non-traditional communication back to the user. I may actually be using a smartphone in a regular smartphone app or an email or a web browser at the end of the day to look at my data. When I go, even today, when I go out cycling on my bike, I usually look at my GPS data once I get home. There aren't a lot of challenges to the sort of in situ use of the data because so much of it is longitudinal. So I don't know. The task space is clearly a sort of rich interactive system where you've got to do it. But in that case, the user's not moving much. So maybe if I'd given more thought to what our home application was, because there the person is potentially having a real sort of situated experience, and then in that case I don't know. I'm not a big fan personally of spoken interfaces, but I know they're kind of the thing du jour right now. I just don't like them. No?
So I have one.
Sure.
You've talked a lot about activity recognition, and to be as contrarian as I can, it seems like a lot of time what you ultimately want to be able to do is some kind of intervention. Mm-hmm. And there's lots of cases where you can intervene usefully without having recognized very much per se. Anything from the pacemaker, where as long as you shock a person in a way that their heart keeps ticking, it's fine. You don't need to necessarily know, are they walking or whatever. You just need to shock in a way that their heart will keep ticking. And a similar example is the Stanley self-driving car. Often, one of its major heuristics was whatever you start driving on, it would continue driving on patches that looked like that. Mm-hmm. And so it may know, in some recognition sense, it may know very little, but in a behavioral sense, it's doing quite well.
Yeah, I think what you're saying is that we need to be super careful to not make the problem more difficult than it has to be. So for the pacemaker, the key thing is exertion level. We don't really care if it's kendo or geese aerobics or whatever you're doing. The key is if we can get the exertion level right, we can basically set the shocking thing. So I think that actually speaks to maybe sort of thinking a little less traditionally about what activity is. So like this morning, at lunch you were talking about, inferring, getting ready to do a creative thing. Maybe that is an activity, even though it doesn't really map particularly well to.
In the cooking sense, what you really want to make sure is that I've fried the onions acceptably. And what recognition happens along the way only needs to be in the service of that action. I'm sort of taking the extreme behaviorist stance on what do you need to know about what somebody's doing. You need to know just enough to be able to remind them to take the onions out at the right time, and whether you confuse X, Y, and Z.
I like your driving example quite a bit, because there you're talking about something very, very low level, very sort of like almost like a closed control loop where you're not actually really recognizing anything. You're simply sort of continuing the state. The cooking, I think your counter example doesn't work as well in the cooking because the person has to watch. The person has to watch the onions. Otherwise, they're not going to just magically. They probably have to engage in a pretty predictable set of activities in order to get the onions to the right state. But I like this idea.
Let me frame the question a little differently because I have the same thought, which is what you're saying is that, I mean, well, and put it boldly, nobody cares whether the machine knows what they're doing.
Right.
They care
exactly.
that it does something useful for them, either at the moment or later. And if knowing what they're doing happens to be the best way to do something useful, that's great. But having a full explicit model of what they're doing may turn out not even to be relevant to doing the right thing that's useful for them.
It's worse than overkill. It may not even actually be necessary.
Right, so the question is, you seem to be putting most of your emphasis on getting that model as the important part.
It's true, we are. Yeah, there's definitely, you'll sort of see across all of these that, they're all applications that are around assistance, and as an intermediate representation, we're really trying to up-level from sensor data to sort of notions of human activity. Yeah, that really is kind of baked into this as an assumption. It'd be an interesting conversation to sort of see to what extent actually is that overkill. I don't have a good answer, but it's a really good observation. Stu.
Yeah, I'm struck by the fact that a lot of these applications are these sort of slow, long loop things. And one of the characteristics of people is that they're sort of slow input to the computer, but it depends on whose point of view you're taking. You can get stuff from the machine to the person, lots of bits, and from the person to the machine, low bits. And one way that you try and overcome with this is first input on output. So you give them lots of bits and you point to some part of it. But what you could do is the next level up is input on context. Because your sensors are good at telling a lot more richly what the context is. So I wonder if you can think of any way in which you could do a faster.
So this is a great idea. So the idea that you as the user only communicate something very short, like this right here, this is clean. And then the system can draw huge amounts of data out of the environment to say, oh, well, that's what he meant? Great, let me learn all of that.
Yeah, my classic example is what you'd have to do to order a pizza. So in the one case, you'd have to do the whole address or something like this, or do some complicated thing. The input on output means you see a Google map and you point to the, or maybe not a Google map, you see a listing in telephone directory and you point to that. The input on context would be you just shout pizza into your iPhone and it knows where you are and finds the nearest pizza place and orders it.
Yeah, no, that's good.
So there might be ways of using all this rich sensing stuff to do a context, which then does accelerate a loop.
No, I quite like that. So you tell the person sort of over the course of your day, when you encounter environments that you think have some quality pointed out, and then the system can draw a large amount of information from the context in which you simply gave the bit to say, this is something to pay attention to, in a sense. Rather than sort of saying, these are the 85 things that I like. Just say, I like this, and it can go, okay, well, then let's look at everything around now. And it's an interesting idea. I really like that.
Yeah, maybe it's a health application. And so there's some way you're walking, there's something you're doing. And what that's indicative of is the low medication levels.
Right.
So you put all this complicated information in, and it's going to tell you what to do with the medication.
So this is called input on output?
Well, input on context.
No. What was the thing you?
What's input on context? Input on output.
Okay. Yeah, that's great. I really like that. Anything else?
Steve Draper, like campus official.
Great. Well, thank you.
Thank you.
For more, please visit us at stanford.edu.